Hi everybody, we are starting our second lecture. First, short announcement. Usually the lecture is 2 hours and the tutorial is 2 hours. Specifically today the lecture is going to be 3 hours. Don't worry, we're not going to make 3 hours straight, we'll have a break. And the tutorial is going to be 1 hour. And we'll modify it on a weekly basis. Great. So, last week, we considered the following problem. We had a string of particles. Now, this string of particles was symmetric. It had a specific Hamiltonian, which was a summation. N goes from 0 to n minus 1. En squared divided by 2m plus 1/2 summation r goes from 1 to r kr sum n goes from 0 n minus 1 un plus r minus un squared. This Hamiltonian included only kinetic energy and quadratic interactions of all the different particles up to level r. We managed to diagonalize this, and in the diagonalized form we obtained that it's just a bunch of harmonic oscillators, right? And the omega of each of the harmonic oscillators depends on some parameter k, not this k r over here. Basically transformed everything into a discrete Fourier form, and this omega of squared k was 2 of m, sum of r goes from 1 to r, kr, 1 minus cos of r, ka. And what is most importantly, in the limit of ka smaller than 1, we obtain the linear dispersion relation. Omega of k was c multiplied by the absolute value of k. Now, those harmonic oscillators are simply phonons. The same phonons that we studied in the class on statistical mechanics. And you probably seen these phonons in other cases. The most interesting thing out of this is that the velocity of sound in this dispersion relation, we can actually calculate it explicitly. And we calculated it, and it was simply a square root of 1 over m summation over r k r squared, and r goes from 1 to large r. The point of this exercise last week was to describe to you that when I start from simple minimalistic models, sometimes I can completely describe what the behavior is. I can, moreover, obtain some global behavior, not microscopical behavior, but global behavior, because what it means is that I have specific oscillations of this string, and I can describe to you the frequency of those oscillations. The frequency of those oscillations depends, of course, on the k vector, and then the velocity completely defined by all the different krs in the model. So this minimalistic picture, where I know everything about what happens on the microscopical level, eventually leads to a macroscopical behavior, where I know also again everything, because this velocity of sound completely defined by these interactions, and the interactions are provided by these k of r. Now, there was a claim why I need only small k's, etc., etc., and the claim was, oh, actually, this limit of k of a smaller of 1 is the dominating limit in the low temperature limit. Basically, when I'm looking on the system at low enough temperatures, this macroscopical behavior suddenly appears. Right? So those phonons live in the system, although it can be very, very complicated at high enough temperatures, because W omega of k is not exactly a linear function of k for all the different temperatures in the system, but in general, for low enough temperatures, only the small k limit lives or survives, and we explain it by using the occupation number. And eventually, this is a very simple theory of phonons at low temperatures. Now, why I described it to you, just to make out of a point, The point was, you can solve microscopical models and obtain from them a macroscopical behavior, okay? Like in this Mexican wave example. And usually, or at least in this example, the interactions are such, actually, although they can be very, very complex, because I can make out of those KRs whatever I want, but eventually, it's only a specific limit that survives, and this limit might be not very difficult to track. But in a lot of cases, I don't have this representation. Okay? In a lot of cases, my Hamiltonian is not I cannot simply diagonalize it. In a lot of cases, I cannot simply talk about just some distortions, which were those un plus r, but I have to talk about something else, like magnetization, or the phase, or I have to describe some tensor dynamics. Depends on the system. And the idea is how I can not deal with microscopical representation, but actually jump into some effective representation of the system without the need to diagonalize everything. Okay? So the advantage of the method, we know everything. Sometimes we can diagonalize the Hamiltonian, and if we succeed, we know exactly how the different parameters of the system depends on the microscopical form of the interactions. Right? Now, the other way is, well, let's try and do it without the knowledge of the specifics of the KRs that I have in the system. And the idea is, well, if you look on the same string of particles, and this string of particles eventually will be described by some of the particles are a little bit close by together, some of the particles are distorted a little bit far. And instead of looking on each and single particle, I want to perform a coarse graining procedure. What do I mean by coarse graining procedure? For my coarse graining procedure, I would say I look on a specific window, okay, of my system, and instead of saying there is particle number 1 and number 2 and number 3 and number 4, I assign a specific number. So this is position x, and I assign a specific number to all of those particles together. And I will call it U of x, and this is my field. More specifically, I can do the I perform this operation in the following. So let's look on U lattice of x. So what is this? This is not this field that I'm talking about. This is simply describing all the different positions of my particles on my single line. Okay? So it is a sum over n, U of n, delta x minus na. Okay? So U of a lattice is telling me, well, you have a particle or you don't have a particle at different positions on your lattice. Okay? So if you're not on the lattice, if x is not on some lattice point, there is no delta function and there is no contribution to the field. But if there is a particle at some specific x, or I'm sorry, if this x sits on a specific position of the lattice, I have a delta contribution to my u lattice of x. Okay? So it's basically u of lattice of x is for each lattice spacing. If there is a particle, I have a delta contribution. If there is no particle, I have 0. This is u of x, u lattice of x, as a function of x. Now, when I have written my field in this form, I haven't neglected anything. Okay? So for each particle, and particles are sitting just in specific positions, okay? They can go a little bit to the left or a little bit to the right, but for each different particle, I have a contribution, and all the particles are accounted for, and I know exactly where all the particles are located. The field is performed by the following procedure. So I don't really want to know where all the particles are. Why? Because eventually, what I'm interested in is some sort of macroscopical behavior. So for this macroscopical behavior, the positions or the specific positions, microscopical positions, are not really important. So it's just some correlations or interactions between different particles that have to contribute to the eventual macroscopical picture. So what do? I average, as I told you, over different positions in order to create my field. How I do it? So u of x will be an integral from minus infinity to infinity of some window size WL x minus x prime u lattice of x prime dx prime. So what do? I go over all the different positions of my particles described by this lattice of x, okay, and I integrate in a specific window of size L. Okay? So this WL of x has to be greater than 0, and an integral from minus infinity to infinity of WL of x dx equals 1. So think about it as some sort of averaging going. So this is x. I'm going in all the different positions around x, and I'm producing to you one single number. Yes.
Shouldn't the UN be inside of the delta to show how it's moving? Because according to this, you just
no. So only specific positions are accounted for. You see, so u lattice of x produces to you a delta function, and the size on the size and the weight of this delta function is un.
Oh, so you're basically okay, I understand. You're measuring the sum of
exactly.
the changes, not the sum. It's just the drawing made it seem like you're measuring the amount of particles.
No, I'm not measuring the amount of particles. I'm saying at each position there is a contribution due to the presence of the particle. What is the size of the contribution is un. Okay, and because I want it to be eventually after this procedure, I want to be everything continuous, I'm including delta functions. Right? Any other questions? Yes.
This assumes that the U lattice assumes that we have a binary contribution or something like it either UN or 0.
Yes. Yes. So you remember my original idea was that I have particles sitting on a lattice. Okay, they can move a little bit, but those are the contributions.
Okay, and what if we have a system that is more complicated? We will have
So give me the more complex, I will contribute another delta functions over here. That's it.
So it's just a summation of it.
Exactly. So this is simply averaging over a specific region, because what is this W? Is I can use whatever W as I like. The idea is I somehow average over a small region, well, over some specific region around each x. So for example, I can use what is called top hat. So WL of x is 1 over L if x is smaller than L over 2, and it's 0 otherwise. Okay, so basically looking at some specific positions, I'm counting all the different particles and their contributions from U of lattice of x. I sum them up, okay? I divide it by the length of this region, and that's it, and I produce a single number at each given x. Or I can do different kind of averaging, right? I can do, for example, Gaussian kernel. Okay, so for the Gaussian kernel, WL of x is going to be 1 over square root of 2 pi L e to the power minus x squared divided by 2L squared. Okay, I'm looking on a specific region. I'm putting a Gaussian distribution over here, okay? And I'm saying U of x is just, well, whatever contributions are getting inside my Gaussian, and each UN will contribute proportionally to the distance multiplied by the Gaussian. So where this guy who also, probably some of you studied also electrical engineering. So whatever I'm doing over here for electrical engineers is called low pass filter. Okay? I'm forgetting about all the different information that is far away, and I'm concentrating only on a specific region around my point x. Okay? The size of this region usually is defined by this L over here, okay, or over there, and it's an averaging procedure. I'm not looking on the contribution from one single particle. I sum them up somehow, several of them, and then produce a single number. Yes?
For both things, if L is small enough, I return to the case of one single particle.
Exactly.
So that's the point. So
Exactly. So if L is very, very small, eventually I will have a contribution from one single particle. And since I produced an integration, I will get rid of this delta function and I will get a number. Okay? Now, my assumption always is that this L have to be larger than the lattice spacing. I don't want to look on the microscopical behavior, but it also has to be smaller than the macroscopical picture that I'm interested in describing. So for example, in our phonons, we know that they will have some wavelength, okay? And this wavelength is lambda. So I cannot average over distances that are much farther than the wavelengths that I have inside the system. Why? Well, because I wash out all the effect. So the point is, and this procedure called coarse graining, the point of coarse graining is, let's produce, instead of specific microscopical information, we'll produce some averaged coarse grained information that I call a field, okay? This field have a specific number or a specific value at each x. It's a continuous function, can obtain different values at different positions of the x's, okay? But the averaging is forgetting about the microscopical behavior, but it's not too large as of to wash out eventually the interesting physics that will appear somehow later. Okay? How much specifically or how much exactly to coarse grade? Well, it depends on you. Great. Now, so I have this U of x somehow. The problem when I coarse grained that I washed out specific interactions, but I still don't care. And in a second you will find out why I really don't get it. Okay. Now, next thing was, for our microscopical model, we haven't the field, but we had all the different positions. So we took our Hamiltonian, we had an Hamiltonian, and we somehow diagonalized it by using a Fourier transform. Now, in the field theory prescription, the moment that you averaged, you forgot about all the microscopical interactions that you had, right? So in the Hamiltonian, I had those KRs. K1, K2, K3, K4, K5, interactions with the nearest neighbors, next nearest nearest neighbors. All this microscopical information was available for me. The moment I averaged, I produced this field. I don't have any microscopical information. Right? I don't have anything. So somehow I need to introduce into the model or into this field description the microscopical information that I had before. And unlike the case of microscopical model, in the field theory, statistical field theory, I have to construct the Hamiltonian. Construction of Hamiltonian based on the field U of x. So remember, if beforehand my microscopical Hamiltonian, or the potential energy, was 1/2 a summation of r, k of r, a summation over n, and here I have un plus r minus un squared. So all of this is known in the microscopical prescription. Now I don't know anything. I only know that I have this field u of x. Okay. And the idea that was first, I think, described by Ginzburg and Landau is to say the following thing. We will write our Hamiltonian or potential energy as a function now of our field u. What I mean by that, the idea is, at least for our case of one-dimensional string, is that the potential energy should be an integral over some density of the energy or local density of the energy. I know that I have a field. I know this field describes distortions of my string. Okay? I don't really know how to write it down, my Hamiltonian, because I don't have this information anymore, and I averaged over everything. Okay? But I make some sort of assumptions. So my first assumption is that eventually, well, the interactions are short-ranged. So I averaged over specific values of L, and those values of L include these important interactions. Okay? Now, if I included all the interactions inside my coarse graining procedure, okay, what I assume is that I can write down the total energy as the sum of local energies. Okay? It's extensivity assumptions that enters into my description. So the moment that I have extensivity assumptions, I will just say, so this is everything is continuous, so it's not just a sum of different positions of different distortions. It's an integral over local density of the field. Okay, and this local density in general will be dependent on u of x and dx of u and d squared x of u and all the different derivatives of all the different orders dx. So this is local density.
Potential density?
This is a potential energy. potential energy. So this is the local potential energy, if you can call it. And it depends on the different values of U of x. Okay. Now, I couldn't done it before with this Hamiltonian, because this Hamiltonian somehow, what it tells me, this Hamiltonian tells me that there are interactions not just with my nearest neighbors, but nearest neighbors and nearest neighbors, so the interactions have some extension. The idea of coarse graining is to say, well, you have this extension, very, very, very well, but you averaged it somehow, and it now enters your field, and it enters your effective density of your potential energy, right? This is why I can use an integration, because integration is summation, okay? So extensivity somehow enters inside, and I just push it inside by saying, oh, I coarse grain over some interactions. Okay. Now, what is this phi of x? The answer is, I don't know. Okay. The answer is, I really don't know, because, well, you cannot have everything. You cannot hold the ropes by two ends. You either have all the information and then you're stuck, unless you have a very simple Hamiltonian, or you don't have all the information, but you have general assumptions. Okay? So this approach that we're trying to perform over here, say, we forget about this, we describe it as a field, but we don't know what the density is. But we use some general assumptions to represent this density. Okay? So the idea is, well, maybe I don't know what the density is, but this density has to satisfy some constraints. Or generally said, symmetries. If I have symmetries in my system, my Hamiltonian, my potential function have to satisfy all those symmetries. Okay? It doesn't really matter what the exact structure, but the symmetries have to be satisfied. Okay? So let's look on what kind of symmetries we have to satisfy. So first, spatial translation. What do I mean by spatial translation? If I take this whole string and I shift it by x0, okay, so all the x's are shifted by x plus some x0. Is something happens to my energy, my potential energy? If I just shift the coordinate system, nothing happens. Okay, so this symmetry has to be satisfied. What it means that phi of whatever doesn't depend explicitly on x. Okay. So if I have this symmetry, and usually I have this symmetry if I don't have external fields, I can move my system and look on as a whole, over here, over there, over there. If I don't have external field, it doesn't really matter where I put it. Okay? So there is no explicit dependence on x in my density, because I can shift it anywhere and still the energy have to be exactly the same. The density does not explicitly depend on x. The second symmetry, uniform shift of u. If I'll take all the u's, is my distortion, and I perform a shift, so ux equals to u of x plus c. So think about it. If u is a distortion, okay, this is x, this is u of x, and for example, this is the behavior of my field. I don't really know what it is. Okay. And the only thing that I do, I shift up all of this field for any different axis. And I shift it up exactly by the same amount. what it means? This means that it can not depend, so phi is independent of different terms like u independent of terms like u and u squared, etc., 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 and depends only on derivatives.
What?
On derivatives. Of derivatives of u. Right, so basically what it says, if I can shift everything up or I shift everything down, the potential energy should be exactly the same. The only thing that matters are local distortions. So what matters is how this distortion is compared to the local other distortions, right? Close by. If everything is set up or everything set down, it won't change the potential energy. Okay, so this is 1, 2. The third one.
So there is no terms of u and u squared?
U squared, u3, u to the 4th power, u to the 6th power,
There
etc.
is no such terms inside the...
Due to this symmetry, maybe we'll have a different system where I should have dependence on u. We will see this. Number 3, parity symmetry. So what I mean by parity symmetry, if I'll change all the x's to minus x's. Okay, so I will take my line of particles and I will simply invert it. So if this is 0, this is 1, and then I will say this is 0, and here is 1. The potential energy shouldn't change again, right? Where I do care if x goes to this direction or x goes to that direction. Okay. So when I have this parity, I already know there are no explicit x's, there are no explicit u's and u squares and u to the 3rd, so I only have derivatives. So what happens to my derivative? For example, if I have dxu, and I split it x to minus x, what will happen over here? So it will go to minus d of x of u to the minus x. So it should somehow change, right? So if I have this transition from x to minus x, the derivatives, or at least the first order derivatives, flip sign. Okay? The second order derivatives, dx squared u, they simply go to dx squared of u to the minus x. Okay. So what happens if I would have derivative in my density? The first order derivative will flip signs. This is something that I don't want. The second order derivatives won't flip signs. Sorry?
Minus u?
Minus?
No, no.
Where?
Minus u as a function of minus
Minus x, yes.
Okay.
Thank you. Thank you. So therefore, I cannot have simple derivatives. I should have terms, okay, when x go to the minus x, terms that do not flip their sign, because the potential energy shouldn't be affected by this transformation. Okay. So what is forbidden? dx of u I cannot have. Forbidden terms. Due to this parity symmetry. So I cannot have dx of u, I cannot have dx of u d squared x of u. I cannot have dx to the third power of u dx of u, etc., etc., etc. So anything that flips sign due to this parity transformation is forbidden. Okay.
Wait. Isn't the last term allowed? Because
Uh,
they would all the last term they would be.
Yep.
four minuses, so it
You're
cancels
right.
out.
You are absolutely right. The last term is allowed.
Because if that's not allowed, then dx.
I agree with you. I agree with you. I agree. My fault.
So whatever we're there, it's an odd number. Right?
Mm-hmm. Exactly. Now, so this is number 3. What else can we say? Locality. So number 4. Locality. So this is not exactly symmetry. This is some sort of an assumption. Locality means phi depends on u, depends on local values of u and its derivatives. Right? I don't have known local interactions. The density is defined only by this density at x is defined only by the values of u and its derivatives at x, not at x plus something. Yes.
Why those terms forbidden?
So because the symmetry is not conserved, right? So if I would have different terms, so for example, I can have dxu squared. This I can have, right? But if I have an expression that depends only on the first derivative of u, by flipping everything from x to minus x, the energy should be exactly the same, but there will be a term that will have a negative sign. Okay, so the density is going to be modified, and I don't want it to be modified. So it's conservations of specific symmetries, which are global symmetries, not just local symmetries. And the last one, let's call it 5, analyticity. What I mean by analyticity is that this function phi is analytic. Namely, I can expand it in a Taylor series. There are different definitions of what is an analytic function. For us, this last one means that phi is analytic. I can expand it in a Taylor series. That's it. Okay. So the approach of this field theory to the same problem is, well, take all those symmetries, and use them in order to construct your density. So what exactly is going to happen, right? I'm looking on this phi, I'm looking on my potential of a function of u, which is not a function already, it's a functional, because u can obtain different values at different x's. Okay? And I'm saying that this is an integral from 0 to L of something dx. Inside here, I start to put different numbers. Now, first of all, I'm using analyticity, meaning I'm not going to say exactly what this function is, but I'm going to represent it by a Taylor expansion, local Taylor expansion at each position. So first of all, what are the terms that should get inside? So remember, u and u squared, etc., cannot be inside this phi. So I should start with some derivative du to dx, or already using this notation.
But it can't be dx.
Exactly. So let's make it square. Okay. Let's make it square. Now, great. And in front of this, I will put a number, some kappa divided by 2. What is this kappa? No idea. Those are some parameters that I put inside my Taylor expansion. Okay. So this is a local number. What else can I put inside? And say, let's use another derivative. So the second order derivative. So d squared x u. Is it good enough to put a term that looks like this? So this is k kappa 2, kappa 2. And here I have kappa 4 divided by 2. And I'm claiming that it's not good enough to put this term, although this term is allowed by my symmetry, but this is, more specifically, an integral from 0 to L d squared x of u dx is what? It is dx of u computed only at points 0 and L. So those are boundary terms. I don't care about the boundary terms of my system. I care about the internal energy. Okay? So this is why I shouldn't introduce the second order derivative inside. So or any terms that I can simply integrate out. They will produce some constants that depends on whatever happens at the boundary of my system. I don't care about the boundary, I care about the internal energy. So instead of dx squared, I will put second order over here. Okay. Now I can continue, so I have a second order for the first derivative, I second order of the second derivative. For example, I can put here dx u to the 4th power, and put it here some like k6 divided by 2, etc., etc., etc.
Can you do oh wait, no, but why would you be able to do dx u, the third derivative of u times first derivative of u?
Yes, I could. Yes, I can put additional derivatives of any order as long as they satisfy my symmetries that I plotted before.
And that they're not easily integrable.
Yeah, exactly. Anything that it's easily integrated out, well, we just throw it away because it's boundary terms, though we don't care about boundary terms. Anything that it's not easily integrated out, okay, we keep inside. And this is important, at some point we cut this expansion. So the idea is that all the description can be obtained by not taking too many orders of the expansion of u. And the answer is why? Because we smeared everything. Remember, we coarse grained. So we assume that u is a function that it's not really so the modifications of u are not fast. It's a slow function. Why? We averaged. Remember, the moment that we averaged, u cannot just be modified extremely fast. If it's not modified extremely fast, you don't need a lot of terms in your Taylor expansion. Okay. So this is our energy. Great. Okay, so the thing is that here is some sort of a problem. Why it's a problem? First of all, we need to do something with this guy and describe is it comes to this perspective of microscopical Hamiltonian, yes or no. But the other thing is, look, we plugged inside those terms. This guy, and this guy, and this guy, undefined constants or parameters. In the microscopical picture, everything was clear. Sometimes the mathematical difficulty was enormous, okay, but everything was clear. These are the interactions that coming from those two guys. These are the interactions that coming from the other guys, etc., etc. I knew everything. I could obtain the velocity of sound like that. Not like that, we worked like for an hour and a half, but it was defined in terms of the microscopical parameters. Here, I lost information, I used symmetries, but it's still not enough because, well, I don't really know what those parameters are. I can play with them, I can make some assumptions about them, right? But those parameters are not defined in my field theory. Okay? Those are some parameters, and I keep them as undefined. I don't really know how exactly they depend on the microscopical picture of whatever I have. Great. So let's write down this Hamiltonian. And I want to take two terms, right? Because I'm saying the function u of x, due to this coarse grading procedure, is a slow function. So I would like to look only on just two terms, this k2 and k4. It's 1/2 an integral from 0 to L k2 dx u squared plus kappa 4 d squared u x u squared and all of this dx. Yes?
Can we find the kappas if we return to the singular?
Yes. Yes.
That's one. And then we will know if we took enough terms.
Great, great. So you're right, and it is doable in this simple example, but this procedure, as I describe it to you, it's very general. And in many cases, I cannot simply go to the very simple case. Moreover, when I'm going to this, so you're saying the following. The suggestion is, Stas, you coarse grain over a window of size L. Make this L go exactly to A. Okay. The moment that I do this, my assumption about locality is gone. Because the interactions are not local to one specific point on the lattice, they are somehow spread around it. So you remember?
2A. So my cell unit.
How many?
That depends
A's.
if I know
My answer to you, you need to do several A's, and the moment that you do it, you forget about your small K1, K2, K3, K4. You lose information. You average and you lose information.
And I cannot estimate how much.
You can. We will do it. How exactly that? But in general, when I construct a field by using only symmetries, I don't really know what K2, K3, K4 are. Okay. Great. So look on this, just on this term. So I have taken just the two first terms in my expansion. Remember what I have done with the harmonic chain? So I used discrete Fourier transform in order to show that it's just a bunch of harmonic oscillators. This was a discrete problem. Now we have a continuous problem. So what we can do is to use exactly the same method, right? We have a potential. The moment that we have a potential, we will need somehow to diagonalize it. What I mean by diagonalizing it, to describe as if this is an energy that's coming from harmonic oscillators. So how do we do this? It sounds crazy. Like you have an energy which is an integral. So what are you saying that it's just a bunch of harmonic oscillators? And the answer is use Fourier. Okay, we use Fourier in order to obtain the normal modes. I can use Fourier in order to describe this integral as some sort of a Fourier representation. or a representation in Fourier space. So what do we do? We perform the following steps. Okay. And the steps are, use u of x in its Fourier form. So it's 1 over 2 pi, an integral from minus infinity to infinity, e I k x u tilde k dk. The inverse transform is going to be u tilde k. So this is inverse transform, sorry, the Fourier transform. U tilde k is an integral from 0 to L e minus I k x u of x dx. Remember what two identities we used in the discrete Fourier terms. So first of all, we used that the complex conjugate in Fourier space is just u minus x. So the same identity appears over here. U tilde of minus k equals to u tilde of k complex conjugate. This is due to the fact that u of x is a real valued function. It's just distortion. It has no complex counterparts. And we also can use a delta function representation. So the integral from 0 to L, 1 over 2 pi of I k plus k prime x dx equals to delta k plus k prime. The same two identities were used for the discrete Fourier transform, but here we have everything is continuous, and we use the same identities, right? And what we do is we take all this u of x and u of k, and we substitute them into this potential. Okay. I won't describe to you, I will publish in a summary how exactly all the transformations are performed. It's done exactly in the same way as we did it last week. Okay, just instead of summations, we'll have integrations. Okay. To all those who are skeptical about all the different transformations, I will publish step-by-step derivation. But the moment we do the representations of, instead of u of x, we do representations of u of k. Okay. And another important step is dx of u of x. We use the following thing. So it is d of d to dx of an integral of 1 over 2 pi minus infinity to infinity e I k x u tilde of k dk. We assume that this integral is converging, so we can take this derivative and plug it inside the Fourier transform. So it is 1 over 2 pi minus infinity to infinity e to the power, or dx e I k x u tilde of k dk, and it equals to 1 over 2 pi integral minus infinity to infinity e I k x. Here I would have I k u tilde of k dk. We also use this identity over here. And we do it for the double derivatives, etc., etc. We substitute everything. And after we've done all the Fourier transforms and all the representations, we obtain the following simple result, that v of u equals to 1 over 2 multiplied by an integral from minus infinity to infinity dk divided by 2 pi. And here we have kappa squared multiplied, kappa 2 multiplied by k squared plus kappa 4 multiplied by k to the 4th power u tilde of k, absolute value. Okay. So no derivatives, no squares, No, nothing. Ah, sorry. Now look on this guy over here. It is exactly this. So this is a potential energy, and the potential energy, you take some specific value, u of k, take it to the second power, and you multiply it by some prefactor. Okay. So this is exactly harmonic oscillator representation. The only thing is, again, I have no idea what K2 equals to and what kappa 4 equals to. Right, so if I have a mass density of rho, I can write it down. B of u equals to 1/2, or an integral, minus infinity to infinity, dk divided by 2 pi. Here I have 1/2 divided by rho. Okay, or let's write it down already as 1/2 omega squared of k u tilde of k absolute value squared, and then 1/2 omega squared of k will equals to kappa squared k squared plus kappa 2 kappa 4 k to the 4th power. I will put here rho, and I will divide everything by rho, which is rho is local mass. This is just, again, a harmonic oscillator representation. We have omega of k, etc., etc., etc. So the same picture as before. The only problem is k squared. There is no second power. Kappa 2 and kappa 4 are unknown. Okay. But, well, the same structure. Now, how do I know that I will get phonons out of it? How do I know that I will get phonons out of this description?
Well, you basically just got the Lagrangian for the wave equation.
Right. So I know that when k goes to 0, okay, this guy is k to the 4 kappa, or omega 1/2 omega squared of k goes to kappa 2 k to the 2nd power divided by rho. Okay. And without the half. And omega is just some constant c multiplied by the absolute value of k. Now you can ask Stas, but why k have to go to 0? You have different k's in your integral, right? You have k to the 2nd power, you have k to the 4th power. Why just to take k goes to 0? Why it's important?
In order for K4 to be negligible.
Why? So why can do that? It's an integral over different case, right? Yes.
Because for trial expansion we need to go for the small case.
Why? So the question is, why do we need to go to the small case? I remind you what is u of x? U of x is an integral from minus infinity to infinity, okay, minus infinity to infinity of what? Of this window L, x minus x prime, u lattice of x prime dx prime. So this was our averaging procedure. Okay. Now, I went to the K-space not just because, well, it's exactly the same as I've done for the microscopical model, etc. There is another point over here. I've done this coarse graining. Okay. And this is my coarse graining procedure. Now, after I've done coarse graining, I can go to the Fourier space. Okay, I can go to the Fourier space. And what exactly this coarse graining procedure is?
Convolution?
It's a convolution. Okay, so if it's a convolution, I know that u tilde of k, it is w L of k u lattice of k. Right? This is just a property of the convolution. So remember, we had two different w's. We have a top hat and we have a Gaussian. It's easier to describe it with a Gaussian. So if WL of x is 1 over square root of 2 pi L squared e to the power minus x divided by 2L squared, WL in K space is going to be what? It's going to be e to the power minus 1/2 K squared L squared. And there is some proportionality constant over here.
Well,
actually, no, there is no proportionality constant at all.
also, isn't it because we use a lattice k greater than
So there is a
2 pi
transformation
over
of a delta function, so you don't really care.
2 pi over a is not.
Well, this is really small. This is really small. The lattice spacing is really small. We average it of many lattice spacing. The thing is, as that I would try to say to you is, look on this guy. Okay, so all the different u of k's that enters my integral are of this description. So for any u of k over there, there is a Gaussian multiplication of e to the power minus 1/2 k squared L squared. Okay, so remember, for the engineers, I told you it's a low pass filter. So all the different k's over there, there is a something. So think about this integral. I have an integral from minus infinity to infinity dk divided by 2 pi. Here I have, here it is, kappa 2 k squared plus kappa 4 k to the 4th u tilde. So instead of u tilde of k, I'm writing this guy. So it is w for e to the power minus 1/2 L squared k squared, and here I have u lattice of k tilde. So this prefactor, kills all the large k's. And this is the physical meaning. Okay, so what I done physically, I averaged over everything. So large k's, they contribute, or they come from small x's. Small k's, they describe something that happens on large x's. When I averaged over all the different all the different small values of x, all small distances, what happens is that I lost this information. So the large k behavior physically is the small x behavior, so interspacing positions, they are completely of no interest for me. Mathematically, this is described by this term over here. Okay? So if L is sufficiently large, okay, it's not very small, so if L is sufficiently large, it will kill all the different large k's. So basically, if I have this term over here, I can completely, and L is large enough.
Shouldn't it be squared?
Where squared?
Well, up the entire.
Okay, squared. It doesn't ruin the argument.
It doesn't ruin the argument. It just
Doesn't ruin the argument. You're right, but it doesn't ruin the argument. So if L is large, this guy is very small for large case, and I can completely neglect this term. Yes?
So it means that theoretically, given that we take a W that is different, more forgiving. we will be
So
able-
the answer is, so if you take large W, so this is what engineers call low pass filters, high pass filter. So if you take W, which is a window, okay, the larger the window is in X space, the smaller the window is in K space. Okay?
uncertainty principle.
Sorry?
Uncertainty principle.
Yeah, yeah. The larger it's in X, smaller in K. Now, for Gaussian coarse graining, you see it very, very nicely. You have this term over here, and it's very nice. For others, you can have some small oscillation, etc., but the principle stays the same. In X space, the more you average in X space, the less you care about large case in the Fourier space. Okay? This is the general principle. So, is large excess, small case. Small excess, large case. You averaged over small excess, right? So you don't care about large case. That's it. And mathematically, you see it by introducing this function. Any function that will average over enough space will eventually kill large enough k. Of course, there is a trade-off, right? So there is a trade-off because L has to be large enough. And maybe I have some collective behavior, which is interesting, which happens on scales that is smaller than L. So you have to be careful on how much you average, how much you coarse grain. It's important. Great. So, what is the Hamiltonian that we are left with? So this is our Hamiltonian. This is 1/2 square root omega of k. And we forget about this term.
The half is unnecessary.
Sorry?
Actually, without the half, it's supposed to.
Just this? Yeah. Okay. So we obtain that W of k equals to k or kappa 2 divided by rho squared. Okay. So we have phonons, and we have this.
And K.
What is k? Okay, right. Okay. Very important. So this is c, velocity of sound. So the same, very different formalism. Absolutely different formalism. Forgot about a lot of stuff. We averaged all the different interactions. But eventually, the effective picture is exactly the same, right? The picture tells us, well, what you have phonons, and you can compute the velocity of velocity of sound for these phonons, and you just have some oscillations. This is your collective motion. Right? In all this process, I had no idea what are the different interactions. I had no idea if they are quadratic or they're not quadratic, or if they are just 2 nearest neighbors, 3 nearest neighbors, 4 nearest neighbors. Eventually, the same collective pictures appears. Right? The problem here, and this is the trade-off, I have absolutely no idea what this kappa 2 is. I can assume what is rho, right? Because it's mass of my cell, but kappa 2 I don't really know. I can maybe calculate kappa 2 for a very specific model when I know what the interactions are. But the same picture says to me the following. Well, you don't have to have harmonic quadratic interactions. You can have different kind of interactions. The only thing that matters is when you average, you're capable of coarse graining. You're capable of using all these symmetries, and you're capable of assuming that the interactions are not extremely large, because when the interactions are extremely large, you simply cannot average. You cannot coarse grain. Right? Now, what is better? The microscopical approach, when I know how to diagonalize, great, but I know it for a very specific system, okay, and I can obtain the different behaviors, but only for this one system, or this field approach, where I can say, look, I don't know what are the exact parameters, right, but I know the collective behavior that appears out of this. As long as the local interactions are not too strong, or I'm sorry, not too extended, I can do this, right? What is better? Depends what you want to see. If you want to understand the collective behavior, this is the approach. If you want to study a very specific system, you can try diagonalize it. But I assure you that in most cases, you won't succeed. Because the moment the interactions that we used are not quadratic anymore, you're done. You cannot do anything, right? But I can still apply my field approach. We are going to have a break now for 20 minutes, okay? And we'll continue after the break for the Ginzburg-Landau formalism.
It's not really a velocity. It has like units of that.
Yes, it is. It has to. I haven't told you what exactly kappa 2 is, but it has to. If you compute what are the different, you start from your Hamiltonian, right, regular Hamiltonian, and you use the proper scales and your proper units, you will obtain that this is exactly the velocity of something with the same, because you plug something inside, and if you plug it correctly in the first place, right, using the correct units, you will get the velocity sound in the right units. But you don't have any idea what this kappa is.
Okay, although this omega is frequency, it's not a. Okay.
Okay?
האם ניתן לומר,
כן.
באופן מאוד גלובלי, זה שאם אנחנו רוצים מערכת מיקרוסקופית, אנחנו רוצים לראות מה ההתנהגות של התנועות שלה.
הקולקטיבית.
הקולקטיבית.
כן.
שזה במילים אחרות, מהירות הקול.
במערכת את צודקת, במערכת הספציפית הזאת, אבל כשנראה
איזה מערכות?
אז לדוגמה, אנחנו נדבר עוד שנייה על גינסבורג-לנדאו, שם יש מגנטיזציה, לא מהירות הקול, זה משהו שקורה למגנטיות.
אוקיי, אבל אנחנו יודעים במערכת מקרוסקופית מה קורה למגנטיות, אז אנחנו נצפה לחזור ולקבל משהו שמתנהג כמו מגנטיות.
יפה מאוד, אז עכשיו אני עושה...
זה כזה, מה אנחנו רוצים למדוד במעבדה? ואז אוקיי, אנחנו יודעים מה הקפה מדויק, אבל בסוף אני אדוד את זה במעבדה ואני אגלה מה ה-value של זה.
נכון, נכון.
זה הצורה, כאילו, אני מבינה מה הדרך המתמטית, אבל אפשר לתקוף את זה גם פיזיקלית. כאילו, אנחנו יודעים שככה המערכת צריכה להתנהג.
אבל בוא נגיד שיש לך מערכת מסובכת. כדי למדוד את ההתנהגות שלה, אוקיי? את צריכה לבנות עכשיו מעבדה שעולה לך $3 מיליון, בסדר? ואני, או מישהו שיכול לבנות תורת שדות כאן, יכול מראש להגיד לך, א' כל, כי דברים מעניינים קורים רק שקאפה 2 פה הוא מסוג א', הוא מסוג ב', הוא מסוג ג'. אז כשאת בונה משהו, תשימי לב לעשות את זה, או את זה, או את זה, או את זה.
לא, זה כן, אבל כאילו, שוב, יכול שאני מסתכלת על זה יותר מדי סימפליסטי, אבל כרגע יש לי פרמטר אחד, קאפה 2. כן.
יהיה לך עוד כל מיני פרמטרים.
יהיו, כאילו, זה כזה...
כן, כי זה, תשימי לב, זה מאוד תלוי מה אני אדחף לתורת השדות שלי. זוכרת שבניתי את הפי? אנחנו עכשיו נבנה פי של גינסבורג-לנדאו, אז בפי הזה היה לי קאפה 2 dxu בריבוע, היה לי קאפה 4 d בריבוע xu בריבוע. היו לך פה רק שני פרמטרים ודי מהר הרגתי את כולם.
נכון.
גינסבורג-לנדאו יש כבר 3 פרמטרים. ועוד כמה, כלומר, את צריכה לפעמים לקחת פרמטרים אחרים, זה מאוד תלוי מה הגודל שאת מדברת עליו, באלסטיות זה מאוד פשוט, ונכון יהיה לך רק גלים בסופו של דבר, זו מערכת מאוד מאוד פשוטה, אבל כשאת מדברת על מערכות אחרות, יכול להיות בזמן בניית ההמילטוניאן שלך, את תצטרכי איברים נוספים, עוד פעם, הסימטריות יאפשרו לך להכניס עוד דברים, זה אומר שיהיו לך עוד פרמטרים.
אוקיי, אבל האינטואיציה הפיזיקלית שלי לא שגויה.
לא שגויה.
יש מערכות שהמערכות המעניינות, שבהן אין אינטואיציה פיזיקלית. או לא אינטואיציה היא כזה סאונד
זה נכון, אבל את צודקת בואי נגיד ככה, השיטה הזאת התפתחה לאחר שהסתכלנו על כל מיני מערכות, הבנו מה מתרחש בפנים, אפקטיבית, אמרנו יש פה גלים, יש פה את זה, ואמרנו, טוב, איך אנחנו נתאר את זה תיאורטית, ואז נולדה תורת שדות.
איך אנחנו מגיעים לזה, איך אנחנו מפתחים דרך מתמטית להגיע לזה, בלי לעבור דרך תיאור מדויק של המיקרוסקופ.
בדיוק.
כי אנחנו יודעים מה המקרו.
אנחנו יודעים. לפעמים אנחנו לא יודעים מה המקרו, ואנחנו יכולים לקבל את זה בתורת השדות שאנחנו נפתח.
כן, אבל קודם זה כזה היה proof of concept, בואו נראה על מערכת שאנחנו יודעים.
כי זה פשוט.
שזה עובד, כי זה פשוט, ואז נעשה לזה ג'נרליזציה ונראה מה אנחנו מודדים במעבדה וכו'.
כי בסוף אני רק רוצה לקחת את הרעיון ולהגיד, תנו לי תורת שדות, אוקיי? אני אתן לכם את ההתנהגות הקולקטיבית שיכולה לצאת משם.
עוד שאלה קצרה, אני לא הסתכלתי היום, אבל האם העלית את הספרים?
לא, שכחתי.
אני ממש אשמח, כאילו אני אוהבת גם לקרוא, אני ממש אוהבת לקרוא,
אין בעיה,
אני מסתכלת להקשיב, אבל מספיק שאני מפספסת משפט אחד ואני מאבדת את זה.
אוקיי, בסדר.
סליחה, תודה רבה.
יש לי שאלה קטנה.
כן.
המהלך שעשית פה,
כן.
הוא עוד הסבר ללמה ביטלת את קייב הרביעית, נכון?
בדיוק.
לא
זה לא עוד הסבר, זה ההסבר. כי אם לא היה לי את זה, עכשיו אני לא יודע מה הקיים החשובים. אני אומר לך, בוא ניקח את התחום של הקיים הקטנים, כן? אני אומר לך את זה.
כן.
עכשיו למה? כי יש לי אינטגרל שם. תכל'ס יש לי שם איזשהו אינטגרל, U של K זה כל מיני דברים שאני לא ממש יודע.
זה חלון ממש צר.
בדיוק.
לעומת הגאוסיאן הקודם.
בדיוק. כלומר, ככל שהאל יותר גדול, ככל שמיצעת על יותר, הדבר הזה הוא מדעיך את זה בצורה, כלומר, K קטן, אפילו K קטן, תכניס לפה K קטן, כשאל גדול, הדבר הזה הוא כבר ממש ממש קטן. חוץ מאשר K שווה ל-0 זה 1, K שווה ל-0.1 זה כבר 10 במינוס שביעית, נניח, כן? אז הדבר הזה, ההדחה המאוד מאוד חשובה הזאת, היא הורגת את כל הקיים הגדולים, אתה לא יכול לזרוק את הכולם, זאת אומרת, רק את הסדר הראשון אני אקח, וזהו. זה הרעיון. יש אפשרות פיזיקלית, אתה אומר, רגע, אבל אני מחפש בעצם, זה קשור קצת למה שאומרת. אני בסוף מקבל גלים, ואני יודע שהגלים הם מתנהגים בצורה, כמו שהסברתי לכם שבוע שעבר, הגלים יש להם התנהגות כך וכך, ואפשר להסתכל על occupation number, ומשם מגיע שבטמפרטורות נמוכות אני צריך לקחת רק את זה ואת זה. אבל פה זה הסבר יותר כללי. אתה במרחב פוריה, אתה עובר עליו לא רק כי זה נחמד לפתור כל מיני דברים במרחב פוריה, במרחב פוריה אתה גם רואה, בסדר, מה הגבול הרצוי שאני יכול לעבוד בו. ברגע שעשיתי קורס גריינינג, יש לי הדחה. ככל שיותר קורס גריינינג עשיתי, בסדר? ככה הדברים האלה, ככה הקיים יותר מודחים.
עכשיו, המטרה הממש כללית שלנו, ה-view הזה, זה הפוטנציאל
האפקטיבי,
מקרוסקופי?
הפוטנציאל המקרוסקופי של המערכת. ותשים לב, בפוטנציאל המקרוסקופי לא הכנסתי בשום, אני לא יודע את זה, אבל בשום דרך לא אמרתי מהם האינטראקציות המיקרוסקופיות. פעם שעברה התחלתי מאינטראקציות מיקרוסקופית והצלחתי ללחסן את הדבר. כן, אבל אפקטיבית. שם אני ידעתי, בגלל שהצלחתי ללחסן, ידעתי מה זה זה. פה אני לא יודע מה זה, אבל התוצאה הקולקטיבית היא אותו דבר. למרות שהאינטראקציות יכולות להיות ממש ממש שונות. אז השוני של האינטראקציות האלה, כל מה שזה יעשה, אוקיי? זה בעצם התוצאה. כל מה שהאינטראקציות השונות, הם ישנו רק את הערך של הקאפה 2. תשנה קצת את זה, תעשה אינטראקציות שהן לא רק ריבועיות, אלא בחזקה רביעית, או בחזקת שישית, או בחזקת שמינית, וכו' וכו'. כל עוד הן תחומות באזור מסוים, שאתה לא יכול, כל חלקיק, הוא לא מרגיש את כל החלקיקים האחרים בכל המערכת, בסוף אתה תקבל רק את זה בסקלות מספיק גדולות.
אני קצת לא הבנתי מה יש לנו, מה אנחנו מחפשים, מה אנחנו משיגים את זה. כאילו, את UK
באיזה שעה התחלנו להפסקה?
ברבע.
אוקיי, דבר, כן.
UK אין לנו, כי הוא תלוי ב-U לטיס, שהוא לטיס זה בדיוק
כן,
איפה כל אחד
כן,
כן. את קאפה 2 וכל קאפה שהיא גם אין.
נכון. אבל ההתנהגות הקולקטיבית.
זאת אומרת, הקשר בין אומגה ל-K זה מה שאני מחפש.
אתה בסוף אומר, אני, גם כשנניח, כן, כשהיה לי את ההמילטוניאן המאוד מאוד מדויק, גם שם, בסוף, האנרגיה הפוטנציאלית שלי הייתה איזשהו אינטגרל במרחב K, ופה היה אומגה של K בריבוע, ופה היה U של K, ערך מוחלט בריבוע, אותה צורה. הדבר הזה רק אומר לך, יש לך אוסף של UK'ים, ו-K שלך הוא 1, 2, 3, 4, 5, מה שהם, ויש לך את המקדם הזה. כלומר, זה סכום, האנרגיה שלך פוטנציאלית, זה סכום על כל מיני U'ים, שכל מה שאכפת לך זה U בריבוע והמקדם של U. עכשיו, זה אוסף של אוסילטורים הרמוניים. אם הייתי אומר לך, זה סכום על חצי של אומגה I, X, I בריבוע. זה אוסילטורים הרמוניים. זה לא דבר פה, במקום סכימה אז יש אינטגרציה.
אבל בעצם היינו יכולים גם לקבל שהביאו לא רק U בריבוע, אלא כל מיני...
לא בדברים שאנחנו הכנסנו.
רק אם אנחנו לקחנו
לא, תשים לב. זה, ה-K הולך לאפס, רק גרם לי ל-WK להיות כזה. בגלל שהיו שם נגזרות, הנגזרות האלה תמיד יתורגמו לאיברים כאלה.
לא משנה כמה נגזרות מצד שני אנחנו...
אז לקחנו, אני אפרסם, ויתרתי, זה עוד חצי שעה או 40 דקות לפתח את הפרויקט, אבל הנגזרת השנייה בריבוע עדיין מתורגמת לזה. הנגזרת השלישית בריבוע עדיין מתורגמת לזה. זה יוסיף לך עוד דברים.
רק מוציא ה-K מחוץ. נכון. אבל אם נגיד אמרת שיכול להיות לך גם נגזרת שלישית, זה עדיין בריבוע. אז בריבוע הזה הוא עושה לי עכשיו איזשהו אפקט של...
הוא עדיין יסדר לך את זה. הוא יכניס לך את ה-K. ה-U של K, הוא לא ישתנה.
זה תמיד שיטה. רק בגלל שאנחנו סימטריה...
בדיוק. הסימטריה הפנימית הכניסה לך כל מיני דברים שאתה, ברגע שיש לך נגזרות, אם היה לך מראש, הפוטנציאל שלך היה תלוי נניח ב-UX בריבוע, אז לא יכולת לעשות את זה.
כן, נכון.
לא יכולת לעשות את זה. אבל בגלל שיש לך אך ורק נגזרות, במרחב פוריה כל הנגזרות האלה יתרגמו.
לא משנה איזה שונה באוויר אני אעשה,
כי בסוף אתה אומר זה אלסטיות, זה האלסטיות הזאת.
ואילו כל המידע למערכת זה...
כן, כן.
שזה גם לא באמת יחיפש נקודתית מה המספרים.
כן, נכון. כלומר, אתה תמיד אומר, אני יכול לתאר בצורה מקרוסקופית, אם אני ארד לרזולוציה מאוד קטנה, זה כבר יהיו לי משהו שהוא לא פונוני. אבל ברזולוציה מספיק גדולה, אני רואה את הפונונים בתוך המערכת, יש לי פה איזשהו מהירות קול אפקטיבית, כזאת או אחרת, וזהו. ממה בדיוק מושפעת, אותה מהירות קול זה כבר עניין מיקרוסקופי, אני יכול להשפיע עליה איכשהו, אבל זה כל מה שמעניין.
אנחנו מתעניינים בהתנהגויות, לא בהכרח...
collective behavior, זה מה שאנחנו רוצים לעשות בקורס הזה. כן. לא, פשוט גבינטות.
יש פשוט את הקורס של...
אפרת? של יונתן? לא, אני לא אעשה גבינטות, אנחנו נלך ל-RG. לא, מכניקה סטטיסטית, RG, סכומים, large deviations.
אבל אנחנו נגיע יש תורות...
יש גינזבורג לנדאו, ואנחנו נראה מתי גינזבורג לנדאו מת, ואז אנחנו נתחיל לדבר על normalization group. באמצע אנחנו נדבר על... לדוגמה, אנחנו נדבר מה זה large deviations, ומתי מקבלים כל מיני תוצאות, אבל זה יהיה ברמה הקלאסית ולא ברמה הקוונטית. והרעיון של תמיד יהיה, אנחנו רוצים לקבל collective behavior. הרבה פעמים אנחנו יכולים לקבל את זה עבור מערכות שהן לא נראות פיזיקליות מתות כאלה, מערכות אקטיביות וכו', אבל הרעיונות נשארים רעיונות. אני רוצה לדבר על רעיונות איך בונים תיאוריה ומה אפשר לקבל מתיאוריה, פחות טוב, נלך לחומר הספציפי הזה.
אני יכול לא לצפות.
כבידות לא יהיה מאוד, יש דברים דומים. כאילו, כי הרעיונות הם דומים. יהיו לך דברים דומים שאם אתה למדת תורת סטטיסטית, אז אתה תראה, זה מגיע מפה והרעיונות האלה. יהיו דברים. אבל סקיילינג לא כל כך יש לך שם. פה רנורמליזיישן ופרקטלינג, דברים אחרים.
אז לקחתי גם את הקורס של אפרת, אז זה יהיה לי השלמה מושלמת.
כנראה, אני מקווה.
אני חושב שזה יפריע לי.
זהו, אבל מי איך לך?
אני חושב שזה יגרום לי אחד להשקיע בזה פחות עמיקה בגלל שיש לי עכשיו סמסטר קצת.
יש לך בחירה?
יש לי 3 קורסים. אצלך אמור להיות מגיש אמור לעשות את שיטות ניסיוניות, כן, משהו עכשיו לזה אני חושב. לפי התגובה שלך.
לא, אבל אני לא זוכר שזה היה באופציה.
זה אפילו בתור אופציה לי קורס. זה אמור להיות. ועוד קורס בחירה שאני עושה של...
יש לנו פיסי ניסיוניות.
סמסטר ב'? לא, יש לי פיזיקה מעשית. כן, בעוונותיי. סתם, בגלל זה עשיתי בסמסטר א', חשבתי שגם שלכם זה סמסטר א'. לדעתי סמסטר א', כל הכבוד. כל הכבוד.
אני די בטוח שנרשמתי מתקדמת
משהו ניסיוני. שיטות משהו
יום שלישי ב-9 בבוקר עד 12.
נשמע שזה קורס כאלה. ישן.
שאני צריך להשלים.
זה עכשיו פה.
אז זהו, יש לי חוץ מזה קורס בחירה במחלקה למתמטיקה, קורס בחירה תורת הרשתות.
זה המון, מה?
עד קורס
4,200. המון.
אמרתי, יש לי סמסטר נאצי קצת. You have the... בקיצור, כן, אמרתי, יש לי סמסטר נאצי קצת.
לא, זה מניח קשה להתקדם.
אני יודע. מאוד מאוד יקשה עליי בסמסטר הקרוב, הבעיה היא גם שהזאת שאני עושה איתה חטיפה, היא עוזבת אותי. עוזבת.
צריך...
אז היא כבר שלחה לי את המערכת שלה, ואני כבר צריכה לעבור עליה, אבל זה גם מתל"ב, ואני לא זוכר מתל"ב. עכשיו בעייתי, כי אני מתרגל קורס במתל"ב. מה סטטיסטית? לדעתי מה סטטיסטית? שפה מתקדמת. כן? מה? פייתון עושה את כל מה שאתה עושה. לדעתי אינטואיטיבי יותר. ואני חושב שאומרת להם אתם פייתון עובד. גם פייתון חינם. לדעתי אין שום סיבה שבעולם עושה מתל"ב. תקצוץ בזה שהרבה אנשים משתמשים במתל"ב. או מנסה להמשיז אותי.
שזה יעור.
אני לא מבין. לא מבין. של דבר. וואו. זה גם שפה שאני נכתבה בשביל להצבן. אני לא יודע.
אתה ממש חושב שאתה משמעות לך.
עכשיו, ביי נגדה. אוי, לא. לדעתי בגלל זה קצת אוברוויל. קצת יותר מדי.
יש קורס מטלב השנה? חשבתי שבדיוק תפוס מטלב. יש את יש את האנליטה.
זה מבוא פיזיקה הכי שמוביל. אבל יש ואז בסוף יש שזה 3 הרצאות.
ואחרי זה גם יש את הפיזיקה
האנליטית, שזה באליזה נומרית.
זה נומר.
באליזה נומרית הוא לא מלמד שום שפה, הוא אומר ששפה שלך.
לא, בשנה שזה היה, אני שעשיתי הוא כנראה היה רוצה שנעשה מטלב.
נר במעלה נתפסו
בשנה שלי זה היה מטלב, אפילו כמו הוא רצה שנגיש את הזה ככה שבמטלב אתה יכול להוציא את זה לא, אבל כמו כל הדברים כמו איך בונים פונקציה, כמו תרגולים היו במטלב המבחן היה כזה
תרגולים בכלל באנליזה נומרית היה שנה
אנליזה נומרית, זה היה מטלב בעיקרון
זה היה מטלב, אבל הוא אמר שאם אפשר צריך לעשות את זה...
כן, אבל כמו כל התרגולים היו כמו משהו לימד, התרגולים עצמם
אני גם הייתי במיפוי
היו על מטלב, אבל בעיקרון אני עשיתי נראה לי 2000
אבל תרגולים אפילו לא
אבל פעם כן היה קורס למטלב
כן, פעם היה קורס ממש מעצלב, אחרי זה היה קורס אקסי, ואחרי זה היה קורס CPP
לא, מה קרה זה, הקורס של פיזיקה מחשבים בעצם היה רק C++.
כן. כשאנחנו למדנו זה היה CPP ומטלב.
כן, שאני למדתי זה היה שנה שהתחילו לעשות רק C ומטלב, כי מה קרה זה היה קורונה, אז כולם דחו את מטלב להיות בקיץ, ואחרי זה הייתה את הסגר השני, אז זה היה שוב מקוון, וזה היה ממש שבועיים וזה. ואז עשו שוב, ואז עשו מגישה אז בגלל זה עשו את זה ככה שכל החובר של התור היה את הפוינטרים, כן. לא למדנו פוינטרים בכלל, בגלל שעשינו מטלב, פוינטרים.
אנחנו למדנו, כשאנחנו למדנו בקורס, אנחנו למדנו CPP ומטלב. אנחנו למדנו CPP ברמת הכלכלה, אז אנחנו לא למדנו
אז אמרנו טכנית זה היה C++, כמו זה היה C++, כמו כל הפורם היה C++, אבל כל הדברים היו דברים שהיו של C. אולי למדנו קלאסים, אני לא זוכר אם למדנו קלאסים. כן, בדיוק, זה למה אני מנסה את זה. בדיוק, זה למה אני מנסה.
אבל כן, אבל הייתם CPP קלאסים, אם למדתם קלאסים.
אני יודע, אני לא זוכר.
זה יותר מתקדם פוינטרים.
אני יודע. כן ולא.
בשביל להשתמש בפונקציות מורכבות אחת פוינטר. ודאי, זה פונקציות שאתה רוצה.
אני לא זוכר.
קלאסי זה כבר ממש להתחיל להיכנס לשפה.
לא, אבל יש קלאסים כזה, אתה יכול לדעת את הבסיס של קלאסים שיוצא עכשיו וזה אתה יכול
לומר, אתה יש לך קלאסים.
So, while we have obtained the general information, and we hopefully understand now that there is a trade-off between having all the microscopical information and having very little microscopical information but knowing only the symmetries, both paths leads to exactly the same collective behavior. When you use fields, you can obtain these collective behaviors, but you don't know what are the exact parameters because you coarse-grained. Or when you have microscopical description, you can only solve it for very specific cases, simple enough cases. Okay? So it depends on you what you want to do. You want to solve a simple case, or you want to solve a more general case, but then you don't exactly know what your parameters exactly are.
Is kappa 2 related in any way to the kappa in the microscopic?
Yeah, if you have, so there is, you can obtain exactly this kappa 2 to this kappa that we obtain in the microscopic behavior.
Oh,
okay. So what we are going to do now is to apply the same formalism or the same ideas of constructing a field-dependent Hamiltonian for order and disorder in the case of magnets. And this is actually, all of this was developed. So we're going from microscopic order to the Ginsburg-Landau. So this is what we are going to do now. The idea is as follows, and maybe it's related to your question. I know that for magnets there is some interesting behavior that occurs as a function of a temperature. Okay. So I know if I'm looking, well, let's assume that I have a magnet, and this magnet is described by spins that pointing in different directions. And they also interact with each other. I know that if I'll measure the total magnetization of my system, okay, so what is my magnetization? Let's write it down. So the magnetization is 1 over the volume sum over I. I'm summing up all the different spins that I have inside my system. Mu I, the value of the spin, multiplied by some n. Okay. And this is the direction that I want to measure the application of the magnetization. So I know, and this is a function of temperature. So I know that for high enough, or at least if you're taking my class in statistical physics, we discuss it by the end of the class, or the year, is that for high enough temperatures, the magnetization is 0. Okay, and we have paramagnetic phase. Interesting behavior starts to appear at a point TC. Curie point, not Madame Curie, her husband, Pierre Curie. And below TC, the magnetization is non-zero. It can be or positive, or it actually can be negative. Okay. Depends on your initial conditions, how exactly the system what exactly the system state was when you cross this critical temperature, the TC, and here you are in a ferromagnetic case. Ferromagnetic phase. And the idea of Ginsburg-Landau was, I want to describe this transition, although in the same way, or what happens in the vicinity of this transition, in the same way as we describe this elastic behavior, right? The idea is there are some interactions between the different spins, right? We can take an Ising model, okay? We can construct what are the interactions between the different neighbors of the Ising spins, okay? And there are some sort of interactions, nearest neighbors, next nearest neighbors, etc., between the different spins inside the system. Okay? And maybe we can construct the Hamiltonian, and maybe we can diagonalize it. So this is the direct approach. Give me the model, give an Ising model. Okay, give me the exact interactions, and then I will manage to solve it, maybe, and describe what happens to the magnetization of the system. The problem with the Ising model is that it can be solved for specific type of interactions in 1D. It took something like 30 years, and even Landau, the great Landau, couldn't do it. It was done by Lars Onsager, who did it for the first time in 2 dimensions. In 3 dimensions, or 2 dimensions with field, in 3 dimensions, nobody really knows how to solve exactly the Ising model that was introduced to you in the undergrad studies. Right? So I can do something with the specific types of models like the Ising model and study this transition from paramagnetic to ferromagnetic. The idea of Ginzburg and Landau was, well, I don't really want to go into this direction. What I want to do is to perform some sort of cross graining, because eventually the order of this magnetization is not just, well, two spins point in the same directions and everybody else point in some other directions. We are in the thermodynamic limit. So there's a huge number of spins. So if I'm sitting in this point, means that big portion of my spins inside my system are interrupting somehow to create this collective behavior, this collective order that's coming from completely isotropic interactions. And then I say, well, if I would construct a field and I use the same ideas of symmetries of how to construct the Hamiltonian from this field, maybe I can obtain a general information of what happens here. I might not have all the parameters, or I don't really know what the different parameters are, but I can maybe describe this transition. Okay? How exactly it happens, what happens, why it happens. Okay? So the idea of Ginzburg-Landau is not to say, let's solve the Ising model. People have done it. It's very, very difficult, and it can be done in a very special cases. Okay? Beautiful models, extremely beautiful techniques of how to solve different Ising models, but it's in some sort of dead end. What I mean by dead end, you can analytically solve it for 5, 3, 6 cases. That's it. Okay? And it will take you a lot of time to do something new. But the field approach, well, can be maybe useful. So this is what we are going to do. We will take Ising model as our standard model or idea. We will coarse grain it. Okay? We will coarse grain it and we'll build a field. And afterwards, we'll introduce symmetries and we'll build a Hamiltonian. Okay? Out of this Hamiltonian, we'll try to see how exactly this critical temperature occurs at all. Maybe the field theory will fail, right? Who knows? So the goal is to describe this phase transition using the ideas of field theory and Ginzburg-Landau field and Hamiltonian. All right, so what do we do? First, think about the following problem. Let's assume that we have a lattice. It can be 3-dimensional, n-dimensional, doesn't really matter how many dimensions we have. And on each point of the lattice, we have spin that describes the magnetization at this specific point. Okay. The value of at lattice point I, there is spin mu I. And you can assume that it can be either +1 or -1, or it can have different directions. It's going to be then a Heisenberg model. It doesn't really matter, because what we're going to do, we're going to coarse grain somehow different lattice sites. Okay? Coarse graining. This coarse graining procedure, exactly as in the elasticity, it produces a field. Okay. So first of all, remember, have we done the coarse graining for the elastic part? We said, well, we have something that's going on the lattice. Okay. The same goes over here. So there is a magnetization that I would call it M of lattice, and it's just a sum over I mu I delta x minus Ri. So those Ri lattice points. Okay, so this is an explicit description of the magnetization, okay, or the spins values on different lattice points. I haven't neglected anything. Next, what we do? Well, we define a field. What is this, our field? M of x. It's an integration. Let's assume that our lattice is not two-dimensional, but three-dimensional. D3 over x W L x minus x prime. Here I have M lattice x prime. What it basically means that I look, so here it is specific x. I look in a region of size L to the third, okay, and I do something with all the spins inside my region. And then I assign one single value to this x. Then I move to another x. I do the same. I move to another x, I do the same. I move to another x, I do the same. Okay? Yes?
Don't think about it like, if I have a particle with magnetization, it will be filled only from this area.
So the field is some averaged value only from this area around this specific x.
So the particle in this field will fill this effective...
No. No, because I haven't told you exactly what I have done. So let's assume that I can sum up, okay, so I can do the following thing. For example, I can say that M of x is 1 over delta v, sum over I inside this delta v, mu I. You can do something like that. It's not an average, right? It's not an average. I just sum them up and I divide it by the volume of my specific region. Okay. So it's not effective filling. I just sum them up and I do something with them. Now, it's not actually enough because so this is the field of the magnetization. What Landau and Ginsburg do, they say, all right, so the idea is that we either in paramagnetic phase or we in ferromagnetic phase, so we need some sense of order. Well, magnetization can be positive, can be negative. I want to see if, or the field is not just this M of x, okay? I want to describe phi of x, order parameter. What is this phi of x? Say, this is M of x, whatever I have measured over here, divided by some saturation. Let's call it M saturation x. What is M saturation of x? M saturation of x, okay, for example, I can say, using this description, is 1 over delta v divided by I inside my delta v of absolute values of mu I. So you see, what I'm actually doing, say, well, I can have a field or average magnetization, but I'm not interested in the average magnetization. I'm interested if they are aligned or they are not aligned. So if they are all sitting together, okay, and they perfectly align, M of x going to be equal to mu M saturation, right? Because they're all in the same direction. So phi of x is smaller or equals to 1. If they are completely disaligned, okay, what's going to happen? Phi of x is going, or are they going to be greater from -1? Right, so this is because so for example, if they're all pointing up, phi of x is going to be exactly 1. If they're all pointing down, they're still ordered, but this order parameter tells us that it's -1. Okay? But if they're completely disordered and every spin in this region pointing in completely different direction, this phi of x is going to be 0. Why to do this choice of order parameter? Sorry? Lama 0? Why 0? Why in half? So think about it. This guy is positive M saturation. M of x can be negative if they are all pointing down, for example. So you have -1, -1, -1, -1. So M of x is going to be the saturation value with a minus sign. So this is why it's greater than -1. 0, if for example, let's just consider that I have only 2 spins. One is pointing up, the other one is pointing down. So what is the order parameter? It's 0 because I sum in +1 and -1. So this order, this guy, is when the field, this order parameter field, is 0. Order, when this field is something that is plus, positive, or minus. I don't care if the magnetization eventually in the up direction or in the down direction. The only thing that matters is that I have total magnetization. That's it. All right? So this order parameter phi, this is what measures if the interactions somehow applied to the system manage to create local order. Okay? If the phi is exactly 0, then there is absolute local disorder, complete symmetry. What I mean by symmetry, so each spin can point wherever it likes. Okay? When phi is not 0, the symmetry is broken. Why the symmetry is broken? So I have a preferred direction. Preferred direction means, well, not all directions are isotropic. I have preferred direction, no symmetry in the system. Yes?
יכול להיות גם מצב שיש סדר, אבל הוא לא מכיוון מועדף, לצורך העניין, כל שני ספינים, אחד למעלה, אחד למטה, אחד למעלה, אחד למטה. בסדר, אבל הוא עדיין שווה 0.
So the question is, well, this is also some sort of order, right? This is some sort of order. Let's assume that all my system, the whole system, is exactly in this state. You're right, it's some other order, but I cannot measure it in terms of magnetization. I have to measure it somehow else. You're absolutely right. This is also an ordered system. Okay, the symmetry is somehow broken. Yes, you're absolutely right. But I won't see it when I measure magnetization. There are systems like that. It's called an XY model. Yes.
Ordered system, but not in the macroscopic sense, in the microscopic.
It is ordered also somehow in the macroscopic state, but I will have to think of different way to measure it.
Well, you can just measure the energy.
It's still called macroscopic ordered?
Yeah. Because think about it, that the whole system like that, it's exactly the same. The whole system is up, down, up, down, up, down, up, down. So there is a specific preference. I can call it an order.
I mean, it's just energy. You can use energy as a because it's an extreme amount of energy.
There are ways of what exactly I have to measure in order to find order inside the system. Yes. It's not the kind of order that we would think about it, but you're right, it's an order. Or let's set it like a preference of a specific state. Great. So we have this field. We define the field. What is the next step? The next step is to construct a Hamiltonian. Construction of Ginzburg-Landau Hamiltonian. So I assume again that my Hamiltonian, as previously, okay, can be described as some integration. Okay. Now here it's integration over the whole volume of some energy density d3x. Now I coarse grained. The moment I coarse grained, okay, I somehow brought everything or all those different interactions to be inside my effective field, okay. And now I just sum up over all the different energies or energy densities that I have inside my system. Okay. So what do I do? So here I have phi, right? I have d dx d phi. I have d squared x phi, and etc. etc. etc.
When you say x, you mean x, y, z, right?
Let's call it x, x. Okay. So derivative with respect to x, derivative with respect to y, derivative with respect to z, etc., etc., etc. Okay. Okay. So in order to construct phi, I use again symmetries. What are the different symmetries that I have in this system? Remember, so I thought about the elastic system. It was analyticity, locality. We changed the x to the minus x, etc. We use some symmetries. So in constructions of Ginzburg-Landau, you also use some specific symmetries. Let's line them up. So first of all, internal symmetry. So what happens if I take the field and anywhere inside the system I will change it to minus phi? Will something happen to the energy of the system?
No.
No, right? Because if I had phi over 0.3 over here, and here I had 0.2, now it's going minus 0.3 and minus 0.2. Somehow nothing will change because I just flipped all the spins. Think about it. I flipped all the spins in the system. Whoever pointed up is pointing down. Whoever pointing down is pointing up. Nothing really happened. So if I had this internal symmetry inside the system, I cannot have terms that depends on phi. Forbidden.
Couldn't you have phi squared?
I can have phi squared.
So it's any odd powers, right?
Phi squared. Can I have phi to the third power?
No.
No. Right? Again, because when I flip, the phi to the third is going to be minus phi to the third. Okay, so not something bad happens. So I can have phi to the second power, phi to the fourth power, etc., etc., etc. Unless, and this is interesting, I have external field. The moment that I have external field, when I flip all the spins, due to the interaction with the external field, okay, the energy is going to be modified, right? So if I don't have external fields, I can only have phi to the second power, phi to the fourth power. But if I have an external field, well, maybe I can have phi. So I know the following. If I don't have external field, phi to the second power, phi to the fourth power, phi to the sixth power. If I have external fields, the odd powers are going also to be present. Yes?
Phi is a vector, correct?
Okay, so phi in Ising, it's a scalar. But in general, I can assume that I can construct a field that it's going to be a vector.
Yeah, but in this model, use a three-dimensional system. So that means even if we were to add an external
Because
field.
it's the field in this position. I can move in the x direction, I can move in the y direction, and in the z direction.
That means if we were to add an external magnetic field, the symmetry will only be broken along one
Along
axis.
the direction of the external field.
So
Okay.
the symmetry would still remain for the other two.
For example, yes.
So if we do have external field, we cannot have phi squared.
No, we can have phi squared, but look, the symmetries only tells you what you cannot have. So if you don't have external field, the symmetry tells you that the energy is not modified when you make phi go to minus phi everywhere inside your system. Okay? So due to this symmetry of internal symmetry of exchanging phi by minus phi, and the energy is not modified, you can say the energy cannot depend explicitly on phi. That's it.
And because we do not know.
But if you have external field, well, this symmetry does not apply anymore. That's it. Well, but the only thing that I'm saying, symmetries, due to symmetries, you cut different terms from the expansion of your energy.
Doesn't this also get rid of all the derivatives that aren't squared?
Oh, great. So we'll go in the second there. We'll go in the second there.
So we don't even have to use the boundary thing.
All right. We'll go in a second there. Okay. So this is internal symmetry. Now this is allowed. So internal symmetry is A. B. Spatial symmetry. So we can take this whole system and rotate it, okay? Right? So we can take everything and rotate it to one direction or to the other direction. Due to rotations, okay? The system, the energy of the system, still have to be the same, right? Because this energy is due to the interactions of all the different spins. So if we take two spins and the whole system of spins and we rotate it, the interactions still stay the same. So if I'm rotating my whole system, the energy should be exactly the same. Now think about it. So if I have kind of derivative of phi. Now what is a derivative of phi? I have a gradient of phi. Okay? So in my case, the gradient of phi is d phi to dx, d phi to dy, d phi to dz. Okay? So if I rotate everything, if I rotate the whole system, okay? So if x prime is some matrix R multiplied by on x rotation. So if I rotate my system, gradient prime of phi goes to R gradient of phi. Okay. So the rotational symmetry tells me you cannot have terms of a grad phi. This is forbidden. What about terms that are grad of phi multiplied by grad of phi, or grad of phi squared? So this actually have a t over here, right? Transpose. So grad prime of phi squared is going to be grad of phi transpose R grad of phi. what is R transpose multiplied by R? It's just a rotation. So R transpose R, it's an identity matrix, meaning that grad prime of phi squared goes to grad of phi squared. So if I have a term that it's not a gradient of phi, but gradient of phi squared, if I rotate my system, it is not affecting the energy. Okay? So great. So we have forbidden, allowed, forbidden, allowed, right? And Ginsburg and Landau said, well, this is enough for me. For my case, it's enough. Okay. Well, the only thing that bothered them is, well, if I have external field, so internal symmetry, spatial symmetry, and C, existence of external field. So if I have external field, I would say, okay, so how the external field interacts. So it is mu, if I have a single spin, it is mu dot B with some minus form over here, right? So I would say that what are the allowed terms? So if the spin are actually pointing in the direction of the external field, okay, I'm going to have a lower energy. Okay? So existence of external field can add terms that looks like minus phi multiplied by some constant. Right? Because I want to lower my total energy because the interactions with the external magnetic field is lowering the energy, so if I'm looking on the field, it's some multiplication by unknown constant h.
Wouldn't it also technically add terms of derivative since it breaks the symmetry?
What other terms?
Well,
so simple derivatives. So first of all, the simple derivatives you cannot simply have because of the rotational symmetry.
But the rotational symmetry will be broken if you have an external field.
Well, it depends. So, great question.
Like it still remains on one plane, but on the other planes it's broken.
No. So what they are assuming is the following. Let me explain. If you don't have external field, let's assume for a second that you're not concerning yourself with the external field. So if you don't have any external field, and you only looking on this energy density over here, phi. So h is a functional of phi. You look on phi, and you say, it's, first of all, I should include phi squared and phi to the fourth. Okay? Why? Well, why not? So you have R, and it's just convention why to write down those prefactors. It's like those kappa 2 and kappa 4 that we used for elasticity. The same goes over here. So we have some prefactor multiplied by phi squared. So this is analyticity. I can expand it, okay, in terms of whatever I have. Plus, I will have u divided by 4 of phi to the fourth order. Okay. And I will explain to you why to take this fourth order and not just to take phi to the second order. Okay.
U over 2?
U over 4.
4.
This is 4. Okay. Great. Now, I should also take the symmetry, spatial symmetry, due to rotations. I should write it down plus a gradient of phi to the second r. So, and they stop over here. Why they stop over there? Because they know that they are coarse graining. The moment that you're coarse grading, the same happens, the same as we did in elasticity. You stop at some specific point and you don't want to take all the different powers of expansion, of the Taylor expansion of your energy density. Because you're assuming the following thing. Your field is a slow function because you coarse grained. It doesn't have very sharp and very fast oscillations. It's a slow function, right? You coarse grained. This means that you don't need very high orders in your expansion. You don't need a gradient of phi to the 4 power, to the 7 power, or whatever. You don't need it. So when you don't have a field, you have this guy. Okay. The question, and this is your question, but what happens if I do have a field? What happens if I do have a field? So you know that when you do have a field, you should have at least this term inside. Okay. And Ginzburg-Landau said, well, I perturb my Hamiltonian density when I have a field by adding this additional term, h of phi. And say, but Stas, the rotational symmetry is broken. Maybe you should have something else. I said, it's fine, this term is present. What you're actually trying to tell me, maybe there are some other terms that should be inside the system. But those other terms are going to be of higher values or higher orders, and I don't want them. So the nice things about the Ginzburg-Landau, they say, I want to write down the minimal amount of terms in my density. There is no limit to how many terms I can put inside, right? But you don't need this because you coarse grain and you want an effective collective behavior. In any case, all those three factors, you don't know what they are. Okay? You don't know what R and what is U, etc., etc., etc. You have some constraints, right? But you don't know what exactly they are. So you say, or at least Ginzburg and Landau said, that's Landau. Ginzburg was added for something else. Landau said, let's stop over here. Because if you can have collective behavior from minimal description, it is enough. Adding additional terms usually won't help you. Because it would only say, well, my field is oscillating faster. But you don't know what happens on those faster oscillations. Because you coarse grain. Yes?
And there's a reason that you write written half of Nabla.
Yeah.
And
so
not like a constant.
All right. So in general, I could put a z over here, right? I could put z over here. But think about the following. If I have d phi to dx, okay, and I'm just renormalizing x to be, or x to be 1 over z x prime, or zx prime. Okay. Then d phi over dx equals to d phi to dx prime 1 over z. So I can always pick up my units for the positional coordinates such that any prefactor over here can be simply cancelled out. Sorry? Okay, great. So why do I stop over here and I do not take phi to the 3rd power? The answer of Landau is perturb it slightly. I will explain you later why I have to take this term. It's important, and I shouldn't have phi to the 3rd. Okay. Now, phi to the 3rd cannot come inside on its own. It has to be coupled somehow with the external field. Okay. Now, you also assume that you do not apply very strong fields. You apply always very, very low fields, because otherwise, if you apply very strong fields, something bad happens. So you apply low fields. So if h is small, okay, and phi to the 3rd is also, well, negligible somehow, it's a negligible term. That's it. But the true answer is, if I forget about this term, okay, forget about this term, I won't have any effects. All the effects inside the system comes from the presence of this guy. We'll see explicitly why. Yes?
Why don't we add the nebula phi if we do have an external phi?
This is his question. Exactly the same question. Why I don't have phi to the third? Why don't I add nebula phi to the sum h? Because I assume that the lowest perturbation due to the external field is the linear part, and that's it.
Okay.
All right.
So
This is I can modify my Ginzburg-Landau Hamiltonian by adding additional terms. Okay. We will see that it won't matter a lot.
So
Yeah.
basically, in the end of the day, it's what works. Like if I make a measurement and I know that it
What
works
is
well,
the minimal description that provides to you the collective behavior that you are already observed in the system? Okay. Yes.
So this was brought by perturbation theory or was brought by the symmetries?
So symmetries and ideas that I need to push inside on the minimal amount of terms. Okay. So it's not the explicit perturbation theorem. It says, well, if you don't have any field, this is what you want to take. If you add field, add the minimal amount of terms that you have to, and this is the minimal amount. Right? That's the story. You can add additional terms, right? And the moment that we'll know and understand how exactly to solve the Ginzburg-Landau formalism, we won't do it today. You will be capable of adding additional terms and studying what is the behavior, the actual behavior that comes out of it. Other questions? Yes.
Is this also still correct when you add a very strong magnetic field, or?
So if you add a very strong magnetic field, something starts to happen. So for example, I assume that my spins, they change only their direction, right? But if I add a very strong magnetic field, they start to move. Okay? They can start to move actually. And then all the Ising idea of what is my model is broken.
Of course,
Itself
would break.
Yeah. So for example, it's some sort of it's called a linear response. When I push a little bit on this, it responds slightly. If I'll push on it very hard, so either my hand will break or the wall will break, but something bad will happen, and I cannot describe the system consistently. That's it. Right? So it's a physical game. I add something and I say that the perturbation is small. Yes.
You have you inserted the effect of the external field as some kind of a linear addition.
Yes.
Will it always be a linear addition because of
It depends on your system. It depends on your system. So there are different classes of theories, and different Hamiltonians can produce different effective behaviors. But we'll see that actually adding something else won't matter a lot. Won't matter a lot where? Near the critical transition.
Okay, but let's assume that I don't want to add it. I want to like multiply all of my unperturbed Hamiltonian by something.
So you're going to have a different field theory, okay? And maybe you can get a different behavior out of it.
Okay, okay.
That's the story. So it depends on what is your material. We're dealing here with some magnets and some order parameters. Let's assume that you look on some anisotropic material and you have liquid crystals. And liquid crystals, they are anisotropic, so you don't have to measure how they align and how they're disaligned. And actually your field is not only scalar, it's already a tensor. So maybe for this tensor you have to bring additional terms. Depends on what you want to measure, what is your material is. But the Ginzburg-Landau formalism is like, even so, just put inside the minimal amount of terms. Because the other terms, they usually won't make a qualitatively different behavior. They will modify some parameters, okay, of whatever you already got for the minimal case. That's it. Any other questions? Great. So this is the Ginzburg-Landau Hamiltonian. Okay, let's write it down. Hamiltonian density. You're absolutely right. So Ginzburg-Landau Hamiltonian density, it's the integration over all of V of r squared to the 2 phi squared plus u divided by 4 of phi to the 4th plus 1/2 gradient of phi to the 2nd power minus h of phi. Here I have d3 to the x. Actually, well, we developed this form for a scalar problem, but Ginzburg-Landau says, well, whatever your field is, just modify it here. If you have a magnetization and your magnetization is a vector and not a scalar, because the Ising spins are not pointing only up or down, they can, like in Heisenberg model, they can point whenever you like. Plug inside the scalars your absolute values of your vector, and that's it. So the Ginzburg-Landau, this is Ginzburg-Landau Hamiltonian. The form of the Ginzburg-Landau Hamiltonian is always like that, but instead of scalar field, you can have absolute values or multiplications of your vectors or tensors or whatever you like. You constructed a field. If you want to write a Ginzburg-Landau Hamiltonian, you write down this form, and everywhere instead of phi, you put your field values. That's it. Okay, so this is the Ginzburg-Landau Hamiltonian. This is great, but we are doing statistical physics. Hamiltonian is not enough, right? What we need to do in order to tell something about what happens in the system. What is the most important quantity that you have to compute when you're treating statistically different systems?
The canonical
Density
ensemble.
matrix.
No. Partition function. Partition function. Z. We need to compute Z. And what is Z? I remind you. Z is e to the minus beta, your Hamiltonian. Okay. And here, we usually put a trace. Trace means a sum over all possible states in your system. You sum for each state, you compute what the Hamiltonian is. You compute e to the power minus beta h, and you go over all the different states of your system. Okay. This is the partition function. The moment that you have a partition function, you can calculate whatever you like. But the most important object is the partition function. You have the partition function, there are a lot of ways of what to do. It's like a machine. You crank it, you rotate the wheel, and that's it. Okay, so we right now know how to construct the Hamiltonian. Okay? The problem is to perform this trace. What is this trace? It's a summation. It's a summation over all possible states of your system. Now, I don't have states because I described everything in what way? Everything in a continuous way. So what do I have here? So my Z, it is a functional, okay? It's a functional integration. So I put it here with some sort of D of phi. And here I have e to the power minus beta h phi. And since we are dealing with Ginzburg-Landau Hamiltonian, here I have Ginzburg-Landau. What this functional integration means.
It's a path integral.
It's a path integral. Okay, but let me explain to you in 5 minutes what exactly I mean by this path integral. So phi is a field. It's a field that lives in 3 dimensions. Okay, but actually, it's easier to describe it in one-dimensional setting. So let's assume that you have one-dimensional Ising model, okay? And it lives on one line. This is x. So phi of x, you can say, well, what is my field? I would say to you, well, your field looks like this. Okay, this is your field. Okay, so if this is my field, I know exactly what my field is. Okay, I plug it inside my e to the power minus h of g of L. For this given phi, I compute this integral, and I have a contribution for, let's call it phi 1. But phi 1 is not enough, because I have to sum over all the different states of the system. This is this functional integral. I have to assume all possible ways of how my field can appear. Okay? So I go and I construct phi 2 of x. And phi 2 looks like this. I take this field, I plug it inside this integral, and I calculate another e to the power minus b of h. And I have to do this, for any possible phi of x. Okay? So any possible not phi of x at a specific x, for all possible x's in my 3 dimensions, and x's and y's and z. So this functional integration, it's actually a crazy function. Or it's difficult to compute, because I don't have to just integrate over here, because you said, well, Stas, how I can perform this integration of a gradient of phi and etc., etc. But it's more difficult than that. You have to assume any possible phi, okay, plug it inside this integral, and then sum over all possible phis of x, all possible representations. Okay. So this is hard problem. Now Ginzburg and Landau, so first Landau, they assumed the following thing. Okay. And this is a brilliant way to solve hard problems is, first of all, you do not plug a lot of stuff in your Hamiltonian, and second, you make some assumptions when you try to solve it. So this is an approximation, and this is what we called a mean field approximation.
Is this similar to the mean field approximation we learned?
Sorry.
Exercise last week, like the one that we usually do.
This was slightly different. There's not a lot of ideas, right? New ideas in physics. It's like you just apply them to many different fields, but eventually the core ideas, there are not a lot of them. So the idea is, well, look on this guy. So I have e to the minus beta h. Okay. Now inside this beta of h, I have a gradient of psi. Now it's not just gradient of psi, it's gradient of psi squared. This means that I have to integrate the moment that gradient of psi is not 0. The moment that this guy is not 0, I have an exponential contributions to the Hamiltonian, okay? That I have exponential contribution to the Hamiltonian that will diminish the value of this e to the minus beta h. Okay? So when grad of phi is not equal to 0, somehow, okay, those situations diminish the value of e to the minus beta h. So Landau said the following simple thing. Well, of course, I have to assume any possible phi of x. I have to assume any possible phi of x. But I know that any phi of x, that it's not constant, okay, it's going to contribute something that will make this e to the minus beta h smaller. So I will forget about all those terms. Mean field phi is constant. Okay. I don't know exactly what this const is. Right? So what I'm saying is that phi as a function of position is going to be have to be constant value. This constant value can vary from one representation to another. So I still have this path integral, but I assume I have a very strong assumption. Due to these negative or small contributions, I will forget about any variations of phi, okay, and I will take only specific cases where phi is constant. Okay, if phi is constant, what is this h? It's just minus v r squared divided by 2 phi squared.
Wait, where did the minus come from?
Forget about the minus. U divided by 4 phi squared minus h of phi.
What hell of an assumption?
Yeah, right? You have to be Landau to do this.
Shouldn't I mean, I'm kind of annoyed about this.
It's interesting. If somebody of you would done it for me in the examination, how would I respond?
I mean, it's really annoying because like the mean field approximation that we learned, it's like, okay, you can still show that phase shift.
It's exactly the same thing.
No, but here you're already assuming that it's constant.
It's exactly the same thing. I'm not assuming that it's constant. I'm assuming that the contribution are coming only for specific representations that are constant everywhere. That's it. It's exactly the same thing, but by using a path integral representation. It's exactly that. I have different representations of phis, and I'm taking only specific parts of it. There are a huge number of different phis. I'm taking part of it.
You accidentally did a phi squared twice. It should be phi to the 4.
Phi to the 4. Okay. And now I'm reaching the goal of my lecture. And the goal of my lecture is that this partition function, it is, well, this functional integral is just, well, cover all the possible values of phi, which is from minus infinity to infinity, right?
Wait, no, it's minus 1 to 1.
Minus 1 to 1. Okay. Minus 1 to 1.
Which is much easier.
Okay. E to the power minus beta v r squared divided by 2 phi squared plus u divided by 4 phi to the 4 minus h of phi v. So this step, it's called a homogenization step. Homogenization step. I assume my field is homogeneous through the whole system. Now there is why, because I'm saying, well, everywhere it's not homogeneous, the contributions of those specific representations is smaller. Okay? Now, the second part, okay, you can say, well, still, Stas, I don't really know how to exactly solve this integral. But actually I do. Why do I do it? Do know how to solve it? Because what is V? V is the volume. Volume of my system. Okay? V is the volume of my system. And I'm assuming that my system is not small, it's large enough. So basically, volume is large number. Large number. I'm not dealing with some small volume mesoscopic physics. I'm dealing with macroscopical behavior. And the moment that I have a large parameter over here, large parameter, there is a very nice technique how to solve integrals which are e to the minus something big multiplied by a function. And this technique is called saddle point approximation. Saddle point approximation. It won't work when you don't have a large parameter over here. So, how many of you studied advanced mathematical methods for physicists?
That's this semester. So
okay. Anyhow, so in the tutorial now, Einav will describe to you how to solve such integrals, but this is a very simple method, right? Very, very, very simple method. I will leave it to Einav and I will discuss it again next week. But the point is that homogenization step assumption leads to eventually to a very simple, actually very simple integral. And the properties, this guy becomes very, very important. And specifically, what's important if these have 1 minima, 2 minima, 3 minima, or the minima and maxima properties, whatever stands here, which is the Ginzburg-Landau density, it what dictates if I have a phase transition, what kind of phase transition would I have, etc., etc., etc. We will discuss it later, but what I want you to remember is how to build the Ginzburg-Landau Hamiltonian. It doesn't matter, it always looks like that, the density. The important part is, well, we know how to solve it for now in one very special case, which is the mean field approximation. You do homogenization, and then you do something which is called saddle point approximation. Thank you very much. See you next week.
Okay. I guess because it's recorded, I'll keep on going with English. Okay. So I understand that Stas talked to you today about writing like a Hamiltonian of some like Ising model or elastic Hamiltonian, but not by looking at all the microscopic states and from this building the Hamiltonian, but looking at some global considerations like symmetries of the problem and stabilities that have to be right. So you had Hamiltonians like this. Sorry, it's not good. Which are functional as M is a field, right? And then you can write a partition function, integral over e to the minus beta, v, which is the volume of the system, hm, dm. Is the size okay? Can you see it from the back? Yeah, okay. And he told you I would tell you how to solve them, right? Okay. So these are functional integrals because this is a functional. And the way to solve it is by using the saddle point approximation. And this would be like the topic of today, approximation. Like what you do in the saddle point of approximation is you look at the minimas of HM, and this is what gives the highest contributions to this integral. And now we will see why it's true, and then we'll solve some examples. Okay, so instead of looking at this integral, we look at some simpler one. So it has this exponent, and we assume that n goes to infinity. And when n gets larger, then this function is it goes down very fast. It's like an exponent that goes down very, very quickly. So the most important terms are the ones that are close to the minima of this function. Okay, so we start by doing Taylor expansion to this function around its minimum. Okay, is it okay right now? So say the minima is x0. So f x equals x0 plus 0.
Shouldn't it be f of x0? You're at x0.
Yes, so thanks. Now this term drops because this is the minimum, right? And now we plug it into the integral. Okay. So this is constant. So we can put it out. Okay. So now we can put the limit minus infinity to infinity, because like the only important contribution is from the proximity of x0, so it doesn't really matter. And then this is just a Gaussian integral, so we have okay, so basically this is the contribution x0, sorry. So this is a contribution of the integral at x0, and this is like some kind of weird look. It looks like some kind of, wait, I dropped the n, some kind of sigma. So this is like kind of it. Okay, it's okay so far. Okay, so basically this shows that in integrals like that, the only important contributions are the are close to the minimal. So when we calculate the partition function, we only have to take into account the configurations of the lowest free energy. Okay, and next week, Stas will show you how to actually do that, and how from this to get like magnetization and whatever. And now I want to show why this is the only important term. Okay? So we do that by taking the next term in the Taylor extension. Okay, so now and again we plug it into the integral. So I just put it outside like the constant already. And this time, to make it cleaner, I'll do this change of variables. This would give like this integral just as -1 over e to the power of minus u divided by 2. Okay. So let me all this. Or this. A. Okay. No, this is it's like this one, okay, except for the 2 sides. Okay. Okay, so now again we expand this to like Taylor expansion. Okay. one, like you have to extend it to 3 integrals. This one just gives 2 pi, and this is this term, okay, from before. Now this one, we have u to the power of 3, so it becomes an odd function, so it gives 0. And this one again gives like some constant, but with a factor of 1 over n. So we can call the result just C, and then we have e to the power minus n divided with square root of n again, and then one plus c over n. Okay, and because we are interested in n goes to infinity, this term vanishes not to 0. This term vanishes very quickly. Okay, so this is why this method works so well. And I want to note that the free energies that you saw and the ones that I will show, they are all analytical, like you can take a derivative infinite times, but so there should be no like jumps at like m or its derivatives, but the minimization process, like when you find the minima of the free energy, this is not analytical. So this is where the phase transition comes from. Okay. Now we will do like a few examples. Do you have a question?
Like when we found out the Hamiltonian in the lecture, we saw that due to symmetrical sum, we do not have the first derivative.
Yes.
Okay, so here we're choosing the minimum, but we don't have to necessarily choose the minimum if because then we won't have the like we even without taking the minimum we don't have the first derivative. So do we have to take the minimum?
Okay, so I assumed we took the minimum, and this is why the first derivative is 0.
Okay. But I'm saying that in the Hamiltonian that we found, we don't have the first derivative at all due to symmetries.
Yeah, okay.
So do we have to take the minima to use the center point approximation, or we are doing it?
Okay, I see your question. Oh, okay. You say that you don't have, like, you have the Hamiltonian, so it doesn't have a term, like, which goes like m. Yeah. Is this what you mean? Okay, but you have many other terms, so the first derivative isn't 0 in any case. You see?
No, it is. We saw in class. We have like other derivatives, power 2, power 4, the first derivative squared. We don't have a first derivative.
You don't have the term.
But it's not the derivative of m, it's the derivative of the Hamiltonian with respect to m, the approximation she did for f.
Ah, okay.
Okay.
Thanks.
You said that something doesn't need to be analytical to find the minimum. Can you repeat it?
Yes, okay. I said that locating the okay, the free energy is analytical, but it's like when you find the minima, or when you take the minima as a function of, say, like the minima of m as a function, sorry, the minima of the free energy as a function of the reduced then this can jump. Okay. I will show examples that show that. Okay, so yes.
Questions. What is with the square root? No.
This 2 pi.
2 pi. Okay. C is a constant.
Yes, it's like what the solution of this integral. So it's yeah.
And another question: the saddle point, is it like a saddle point when we say that the second derivative is also 0? The functions. We find a minima.
Yes.
That the first derivative is equal to 0, and then also the second derivative is 0. Is it the case in here also?
Oh, you mean is it an actual saddle point?
Yeah.
Okay, I think it's called saddle point because it also applies to complex fields, and in complex variables, if you remember, I think you have only saddle points. Wait, it sounds wrong, but okay, specifically with complex fields, you have only saddle points. You don't have minimum and maximum. Okay. Any other?
Good. What is C there?
It's the result of the integral over this. It's 2 pi squared 2 pi something. Okay. Okay. So, and now we will do some examples. Do you remember when I started? At what time?
I think like 56, 58.
No. Okay. So I start with the free energy that matches the Ising model among other models, and I think Stas was supposed to show it to you, but he probably didn't. So I hope it will be clear.
Coarse graining of the Ising model?
No, I just take free energies and show how we minimize them. I don't start over from the beginning like he did. Okay.
No, because he did go up to the point where he was like, the partition function said you go over the south point. We got up to that point.
Yeah. Okay. So he showed the partition function.
Yeah, he just didn't solve for it.
Yeah. Okay. So I'll solve it quickly. Yes.
Why did the second term go to 0?
Because it's an odd function. You have u to the power of 3. Okay. Did you see this free energy?
That's without external field.
Yes. Okay. Okay. So, and now we will find its minima. So, yes.
Don't we assume that the derivative is 0?
No, we don't assume it's 0, but yeah, that's what I was going to say. When we are close to the minima and we don't have external field, then this gives a cost when m changes. So we assume that this
so
is
that's
0.
why we assume it's 0. He was just like, none of this roots.
Okay. So x. Where's m? Okay. So now we take the derivative. sorry, the forms they use look similar. Okay, so we have m equals 0 and u, no, m equals plus minus square root of t minus t over 4u. So this solution exists always, and this one only when t is smaller than 0. Okay, and so now we have 3 minimas, and we want to check the stability. So this way we find which is the minimum and which is maximum. So we take and we can just look at the at 0. So the second derivative is t. So for t larger than 0, this is the minimum, and for t smaller than 0, this is the maximum. And this implies that these are minima. Okay. So now we can look at at like psi for t larger than 0, then it would be just some minima, and in this case, we would have something like this. These are the 2 minima. And m of t would be 0, and then split into 2 options. And where this goes like square root of minus t. And this is the same picture as we got last week, but this time when just assuming this form of free energy. Okay. Am I going too fast or too slow?
So you found the minima.
You want me to say quickly
You
what
just
it
found
is?
the 2 derivatives. You just found the minima.
I found the minima. I found like the extremas, and then I found which ones are minimas and maximas, and through the free energy and the m, and I got like according to this. You think I made some jump? This is what concerns you.
I just don't like if we have more than 1 minima, so we have to do the several approximations several times. We have several possibilities, several solutions.
Okay, it's a good question. When doing the saddle point, we find the minimas. Then I think we take only the global minima. Here we have 2 equal minimas, so maybe there are like twice the contribution.
So you sum 2 solutions, or what do you do?
Yes, you have like you have this thing, so you have maybe 2 x zeros.
Oh,
See,
okay.
and I guess.
When t is greater than 0, what does the other solution of m means?
nothing. There are no other solutions. There is just n equals 0. You see like okay, just one comment. So here, like we do the minimization, and then suddenly it happens analytically, but suddenly we have like 2 minima, and this is what I meant by that the minimization may cause some non-analyticity. Okay. Here I don't put this term at all, okay? Start without it, like the derivative. Okay, so now we added this term, and this means there is no symmetry between m and minus m, okay? So there don't have to be like 2 minima that are similar, okay? Like it would make a difference, and this will cause like a first order phase transition. Okay. So we find the minima. So we have the solution of equals 0. And we have this equation. So we have 2 other solutions by the נוסחת השורשים. Okay, so these solutions exist only if 9b to the power 2 equals 16t, like it is smaller than t. Okay. So again, we look at the stability. Okay, so we will look only at m equals 0. So, okay. So again, when t is smaller than 0, this is maximum. T is larger than 0, this is minimum. So for t larger than 0, there is this minima. You know what? This is t larger than t to the power of 2, 16u. Okay, and have something like this. Okay. There could be another solution here which is minimum but not global. There could be no solution here, but this one is different from maximum, or maybe this is a global. Like this can change by the change of V and also T. And there is an area between that where this is still, there are two more solutions. It would look something like, I don't know, like that. Where this is 0, it's still the minima, but there are two more solutions. Okay. So at t equals 0, this solution just appears. It appears somewhere that is not like the m equals 0, and this is what causes the first order phase transition. Okay. Do you have any questions?
So I'm not really interested in what points exactly is the minima, but how many minimas we have. It's not really interesting.
You mean like that I didn't show what is the actual value of m?
Yeah.
You see, this is like equation with m to the third. You can solve it, but it will be harder than, like, it's not relevant enough like to find it right now.
So we need to think if the minima is m equals 0 or anything else. Because if m equals 0, so we have one minima and that's parabola top, and then if not, we can find one global solution, or we have two global solutions, but it doesn't matter. It still means that we have first order phase transition.
Okay. First, here it's second order phase transition, not first order. Okay. You ask why?
Yeah. What are the names of first order and second order?
Okay. First order phase transition is when there is a jump in the order parameter, like when m changes its value suddenly. So here I'm just I'm drawing something. It's not like I didn't think about it very much, but I guess it would start like something like this, and then at t it would go say like this. Okay. So this is a first order phase transition when the order parameter jumps. Okay, when the order parameter is not non-analytical. Second order phase transition is when the derivative, like of the order parameter, say like this, is non-analytical. Like here there is like in this point the derivative is not defined, but m is well defined by itself. Okay, so this is the difference between first order phase transition and second order. Okay. You want me to wait? be when we have external field. Okay. So in this case, because we have h as a function of x, so we can't neglect this term. Okay. So now we have to find its minima, but it's a functional. So the way to do that is by the Euler-Lagrange equations. From analytical mechanics. So this is the equation. So first we take the derivative of m. So we have Tm. And this is derivative of this. So we have so this is just so this is the equation. It's a differential equation. Okay. Oh. Okay. So the first thing we can do to solve it is to make it linear. Okay. So if we take t is larger than 0, then we know m goes to 0. So we can just neglect this term. And then we have this equation. And then we can plug in like any field and try to solve the equation. I hope we can solve it. And when t is smaller than 0, then m is not 0, so we can't do that. But instead we can do something like the midfield approximation, basically. You can say mx is m plus how do you call that? Something small. What?
Perturbation.
Perturbation, thank you. Which depends on x. And we know what this m is. Even though I didn't erase it. This is m squared equals minus t divided by 4. Okay. Maybe we can say it's absolute value of t. Okay, so now we want to plug it into this equation.
Why does m squared equal to this term?
I erased like the Ising model thing.
So we assume external field in Ising model.
Yeah. Yes.
Okay.
We assume. Okay. Sorry. We assume like the homogeneous equation. This is how you solve a differential equation with some function on the other side. You find the solution for the case where it's homogeneous, like where hx equals 0, and then you add like it's a okay. Sorry. Okay, so now we want to plug it into this equation. And first I want to start with just writing m to the power of 3 and neglecting what we need. Okay, sorry. The mx is of course smaller than m. Power of 3. So we keep only the linear term with delta x.
Can you explain again why h is 0?
This is the way you solve differential.
Okay. Just the homogeneous part of the.
Yeah. Okay. Okay. So now I put it in this equation. Okay. This is 0. Sorry. This and also this cancel with this. I'm sorry that I erased this equation, but it comes from this, okay? So they cancel each other. And then we have and I just put m squared. Now we look at this. So t is minus absolute value of t. We have plus 3 absolute value of t. So this is okay. So this is the equation. for the case where t is smaller than 0. So you see that these two equations are very similar. Like there is a difference in this. Like you have here this factor of 2, but it's not like something very significant. And the only difference is that here it's equation for m, and this is for the fluctuations of m around like the mean value m. Okay, so basically the external field doesn't have like a different effect at the different phases. And in my notes I also have examples of like a few fields, so I'll put it on the model, but I think it's enough for now. Okay. Do you have any questions? Okay, so
יש לך וואטסאפ לקורס?
אני חושב שפספסתי את זה. למה